Today we're going to specifically deal with osmosis, and osmosis is the diffusion of water through a semi-permeable membrane. So before we looked at particles, compounds, molecules, today we are specifically looking at the molecules of water. The molecules will spread out from an area of high to low concentration, just like we talked about in simple diffusion. Today we're going to be learning about osmosis, and osmosis is the diffusion of water through a semi-permeable membrane. Up to this point, we talked about particles or solutes moving through the membrane. Osmosis is specifically water molecules, and these molecules will spread out from an area of high to low concentration, just like we talked about in simple diffusion. Osmosis is a type of passive transport because the water molecules are moving with their own kinetic energy, and there will be no extracellular energy to move these water molecules. So you can see here that they will be able to move right through that membrane. When we start to learn about the movement of water into and out of the membrane, that is determined by the concentration of both water molecules, and also we like to look at the solutes in the water as well. So if there's any salt or sugar or anything like that. The higher the concentration of solutes in the water, the lesser the concentration of waters. And we'll get into that in the next couple slides. But these differences in concentrations of solutes versus the concentration of water create three different types of environments for the cell, which is what we're going to be going over in the next couple slides. The three environments are named as follows: a hypotonic environment, a hypertonic environment, and an isotonic environment. So we're going to start off with a hypotonic environment. So hypo kind of rhymes with low. So hypo, low. This would be low concentration of solute. So even though we're going to be looking at the movement of water, these environments are named after the concentration of solute. Okay, so hypo, low, solute, which would mean high water concentration. Hypotonic environment. So watch what happens. So say we have a beaker, okay, and in that beaker we place one singular red blood cell. The concentration of salt, that solute, inside of the red blood cell is 1%. In the beaker, we have a solvent, or say water, okay, and there is a 0% concentration of salt. So we need to figure out where the high concentration of salt is. Remember, even though we're looking at the movement of water, we're going to pay attention to the solute. So I want to know, where is the high solute, where is the low solute? So here we have 1% salt, so that would be definitely higher than 0, right? So we have a high concentration of salt inside the cell and a low concentration of salt outside the cell. So if you wanted to look at the concentration of water, if we have 1% salt, that means we have 99% water. And if we have 0% salt in the beaker, that means we have 100% water. So 100 is greater than 99. So your high concentration of water is in the beaker, and your low concentration of water is in the cell. Water wants to move from high to low, so we are going to see a movement of water into the cell. So water is going to be moving into the cell through that semi-permeable membrane. You know that there's only so much the cell membrane can hold until it bursts. So that cell is going to start to swell. It's going to grow and grow and grow until eventually, it could pop. And the process of cell popping is called cytolysis. Cytoplasm, lysis, split. Cytolysis, the bursting of a cell. Cytoplasm has burst through the membrane. So who is this good for? Well, if you think about it, bacterial cells, unicellular organisms, the amoeba, the paramecium, euglena, they actually prefer a hypotonic environment because it provides needed nutrients. So with that water is going to come nutrients that these organisms need. Animal cells hate this, obviously, because it's going to make them burst. Unicellular organisms like it, they also, remember, have that contractile vacuole, which could spit out any excess water the cell doesn't need before it bursts. Plant cells like a hypotonic environment because as that water is taken into the cell, it's going to fill up that central vacuole, and it's going to end up pushing on the cell walls and creating what's called turgor pressure, it'll make the cell very turgid, which will only add to plant strength and support. So this it will actually allow the plant to stand upright and it won't wilt over. If the turgor pressure decreases, then you will see a plant droop or wilt because that pressure isn't being exerted on those cell walls. So a hypotonic environment is good for plants, good for bacteria and unicellular organisms, but bad for animal cells. The next environment we're going to talk about is called a hypertonic environment. Hypertonic environment. When an environment has a higher concentration of solute, we call it a hypertonic environment. Think hyper. When you are hyper, you have an excess amount of energy. You're bouncing off the walls. A hypertonic environment would be a lot of solute. Remember, once again, we are naming these environments after the solute, even though we're going to be looking at the water movement. So once again, hypertonic, high solute, which would mean a low water concentration in the environment. So here we have a beaker, 1% salt in the animal cell that's been placed in the beaker, and in the water environment that the cell is in, we have 7% salt. So that would be 93% water if you did the math, and 99% water. So obviously the high concentration of water would be inside of the cell, and the low concentration of water would be outside of the cell. So water wants to move from high to low, so you're going to see that the water is going to move out of the cell. So if water is moving out of the cell, you're going to see the cell start to shrivel up or shrink. And the name of that the process actually has a name. It's called plasmolysis. It's also called cremation, kind of like cremation, but with an N. So it's not the same thing. So yeah, cell shriveling doesn't sound like a good time, and it's not. Animal cells hate this. Plant cells hate this because it's going to decrease that turgor pressure and cause them to wilt. And bacterial cells hate this. So a hypertonic environment is bad for everybody involved. Cells will die in this environment. Our last type of environment is called an isotonic environment. And iso, that prefix, means same. So when an environment has the same concentration of solute and the same concentration of water, we call it an isotonic environment or an isotonic solution. So here's how this happens. So we have our beaker. We have 1% salt inside the cell, 1% salt outside of the cell in the environment. So they're equal. So they would both be 99% water. So there is no high, there is no low. So the water will actually move in and out of the cell, although you're going to see no visible change. The cell will look like normal. It doesn't shrink, it doesn't grow, it just kind of sits there. But water is moving, you just can't see it. Water is in equilibrium already, so it's able to pass in and out. Okay, so if we look at these different types of pictures, you could see what type of environment they'd be in. So our first one, picture A, you could see an animal cell versus a plant cell. You see they look very shriveled, so that would be a hypertonic environment. Our middle cells, group B, they look normal, so that would be our isotonic environment. And you can see in group C, we have our animal cells bursting and our plant cells very swollen, so that would be our hypotonic environment. I will also give you guys a couple links for some Amoeba Sisters videos if you would like some clarification on a few of these topics. If you have any questions, please send me an email. Have a good day. Bye-bye.